Hi everyone, thank you so much for joining us today. Welcome to our August webinar. This month we're talking about multi-sensor systems for structural monitoring. I'm Amna Youssef, I'm the Marketing and Events Executive here at Sensive. So as always, before we begin, I'll just run through a few housekeeping notes. We will be having a short Q&A session at the end of the webinar. So please feel free to type the questions into the question box as the webinar goes along. And also, just to let you know, this webinar will be recorded and sent out to everyone who's registered afterwards. So I'd like to now introduce you to our speaker today, Markus Rennen. Markus has a background as a surveying engineer. He spent a decade in Iceland overseeing comprehensive monitoring projects, including large-scale tectonic plate movements and construction projects. Since 2020, Markus has been a valuable member of Sensive. In his role, he has contributed to many successful wireless monitoring projects, helping clients enhance the safety and longevity of their infrastructure. So, over to you, Markus.
Yeah, thank you, Amna, for the introduction. Welcome, also a warm welcome from me to this webinar. As Amna said, we will be talking about multi-sensor wireless multi-sensor systems, and I'll try to guide you through some real-world examples. So basically, monitoring, everybody listening here will not have to be introduced to monitoring in general. So monitoring concerns a large variety of objects, and basically when we have to observe any object, then we have to follow certain questions, and these questions or tasks, they define what parameters are required to be observed. And of course, when we have to observe certain parameters, they determine what kind of sensor we have to use. So here now a very small example for a monitoring project. We have a construction site here, and this construction site has impact on the environment. In this case, we have this kind of crack here on the road up above here on the area where the handrail is. Right side, you see the handrail here on the photo. And since this is quite significant or obvious what's happening there, the locals are concerned, and therefore there's a request on monitoring, and in this case, some sensors have been mounted to this wall to observe this. So usually then you observe a certain period where nothing is happening. And here on this graph, you see the temperature signal, and you see it reflects also in the journal signal, temperature related or correlated signal in the situation where nothing is happening on the job site. But then obviously at some point, some significant deviation from the common signal happened. And in this case, this was very close to where I live. So I just walked down there and had a look. And then you observe this kind of situation. You see our node here on the wall. That's the blue line here. And you see that some excavation is going on. And that shows that that has impact on the situation. And that means you can trigger an alarm and, for example, introduce or initiate some countermeasures there. So this is how a monitoring project should look like here in small scale. And in case of the wireless situation, we have these kind of nodes that are communicating among each other and relaying the signal from one node to the other to some gateway and then to some monitoring platform. And these nodes, they can contain internal sensors, just like a tilt sensor, for example, or multiple sensors like a tilt sensor or laser distance unit, temperature or so. But also we can connect nodes to external sensors, and then they communicate in the same manner as the internal sensor nodes communicate. And that means that we have a large variety of sensors on parameters we can observe with these kind of systems. Well, when we observe parameters, then we have to somehow figure out how to interpret the data. And there I want to give you this example. That's a about 50-meter high lime oven, where we on the top we have mounted in each direction one tilt sensor node. Looks this way. And we have aligned the axis in a way that all axes or all nodes basically show their parameters tilts in the same direction. Well, when we look at the curves, the graphs we get from this, again, on top we see the temperature curve, and below we see the tilt in the two directions, X and Y direction. And it's quite obvious here, this was obviously a sunny day, and you see the sun approaches from the east, goes over to the south, and then later on comes to the west. And then you see two blue lines here, which are the sensors in the north, light blue, dark blue, in the north, that don't show any of these temperature peaks because the sun, they're never exposed. The north side is never exposed to the sun. The interesting part now is that you clearly see a correlated signal of all these nodes on the top oscillating correlated to the temperature change. And we look closely, you also see the dark blue line with changing with temperature, which means that all the nodes on the top, they're moving in one direction. Now, if we have tilt, then we have to figure out what does tilt actually mean for this. So if this would be a rigid structure, we could extrapolate the tilt over the 50-meter high tower, and then we would have a horizontal displacement here at the top. But we need to verify this kind of sensor model or object model, and therefore a couple of nodes have been installed in a vertical line here. And what you see here in the curves is now that even though the light blue line, which is the lower sensor here, experiences the same temperature change throughout the days, it doesn't move. And so from interpretational point of view, it means that we have movement here on the top. We don't have it on the bottom. So this means we know that this is not a rigid structure tilting, but bending throughout the daily impact. That should just be an example for how to interpret data when you work with it, and you have to know what actually to do with the results. Same situation is, of course, when the circumstances rule what you can see. This is an example from Frankfurt, actually the banking quarter of Frankfurt. In the background, you see the Deutsche Bank tower here. And this is a heritage facade that will remain. And the core will be entirely removed, and the whole facade is just hanging on this scaffolding here. Then there will be excavation about 5 stories deep, and a 270-meter glass tower will be erected within this facade. Now, when you look very closely, you can actually see that there are a couple of prisms here. So this can be observed with total stations, but it's obvious that for permanent total station observation here, there is too much obstructions on the facade caused by the scaffolding, which meanwhile is also closed here to the front. And therefore, the idea was there to mount a couple of tilt sensors and crack sensors. Here you see some in the front. And on the facade, it looks this way, that we have the tilt sensor here and this potentiometric crack sensor to observe the joints in the facade otherwise. So we have an example for different parameters with different sensors observed in the same communication network, meaning we gather all this data, send it to a gateway, and the gateway submits all of this different type of parameters into the same platform where it's then accessible for the experts to analyze and for interpretation. This can be distances like this can be observed by crack sensors like this one here, or of course by laser distance units here on the right side for horizontal rail displacement, or on the left side observations under a bridge in Mülheim an der Ruhr for bridge pillars. Now, monitoring usually is something that many disciplines are involved, and different disciplines, they have different questions. And in many cases, when we're talking about engineering structures, we're talking about civil engineers. So for example, here in this case, we are talking about this is a gym with this roof truss here. And the civil engineers that built this, they have a model for this whole thing. And then, of course, when they have a model, they calculate, for example, loads. And this is expressed in this deflection line, where we have every good presentation has to have at least one complicated formula in there. So we have a calculation of this line. And then you can imagine, if you see this curve, that when it starts tilting, then you have tangent lines, and the civil engineers told us exactly where to place the tilt sensors, so they would be able to interpret the tangents, the tilt of these tangents within the equation, and then calculate backwards, for example, loads when they see that, or the other way around, when they know the load, this and this much snow, for example, accumulating on the surface, then to compare it with the behavior they experience here. So this means that we have an advanced interpretation of the results that we get from our sensor system. Similar situation we have here. This is Thyssen Steel in Duisburg, large steel factory, about 5 times the size of Monaco. And here we have this kind of storage hall where the steel slabs are kept, and they are cut into the right pieces or transported by these gantry cranes into some ovens where they are rolled into sheet metal, for example. And now these gantry cranes, they are rolling on these huge beams here. And these huge beams, here, they are experiencing damages in the past. Now, when you see this is mainly caused by load and then the torsion of the crane or the beam itself. And when you then see cracks here, they can be repaired by patching, welding some patch on top of it, but this can only be done a limited number of times. So at some point the beam has to be replaced, and the situation is this, that they are supposed to last 10 to 20 years, but currently only last about 3 years, and replacement of one of these beams is more than €1 million. So the task was to monitor and see what causes actually the damage on these beams. This has been done in geodetic way, leveling and total station observations, but obviously that cannot be done in that frequency that you can correlate it with the activity of the cranes. And that's why we were asked to install some sensor nodes there. See this here, this is one side beam where the crane is rolling on installation, and the other side is here where tilt nodes have been installed at some crucial places where deformation is expected. Yeah, everywhere. This data then of all these nodes is gathered by gateways with a SIM card, mobile phone SIM card in there, transmitting all the data, in that case in a 2-second data interval onto a server platform, where this data will then be combined with the crane positioning system. During installation, all nodes positions have been measured by geodetic observations, just in coordinates, in order to synchronize the position with the position of the crane's positioning system, so that later on we know exactly what load is on the crane, where the crane was in a certain situation, and what kind of impact it had on its adjacent nodes. In addition, this is the gantry crane itself, and we wanted to observe the deformation of this gantry crane itself. The challenge here was that this system is actually moving with respect to the static installation I showed in the pictures before. And therefore, we had individual networks with gateways here on the cranes installed. Then we could sneak into these holes here and install crack sensors there as well to measure in all four corners the deformation of the crane itself. So not only the situation outside on the beams, but the crane itself. And then, of course, this is the beam. They are pretty large and you could walk inside the beam. And then we knew that there were several areas where we had actually already cracks, and at these areas there were where the patches were already, here is such a steel patch for a crack. We already had, we have two-dimensional crack sensors installed to measure the deformation. On this project, there will be a master thesis from the University, Ruhr-Universität Bochum, be written about this kind of results. I don't have final results yet, but the system, as I said, it runs currently on a 2-second data interval. So we are pretty close to a real-time mode here in observation, and at least the correlation later on will be possible to be determined. The final and most extensive example I have here is from a bridge in Dortmund. Actually, currently in my area, the project with the biggest variety of sensors. This is a major bridge. It's a B1 Bundesstraße, municipality road, 6-lane road, central Dortmund. It's right next to the Dortmund football stadium. And in October last year, I have to check. Yeah, October last year, we installed a number of sensors here. You see the gateway here with the solar panel for the communication. And underneath, the bridge here, 6 lanes, 3 lanes in each direction. And we are looking basically on this picture from this side onto the bridge here. Now, this bridge is pre-stressed, reinforced concrete bridge from 1957. And according to some study that was done in 2022, they already sought or found some cracks in the bridge. And in a construct or a reinforced concrete structure, cracks always mean that there's water ingress. Water ingress causes corrosion on the reinforcement and the pre-stressing cables there. And when a steel cable starts corroding, then the diameter is reduced, and then the stress it can hold reduces, and that leads relatively fast to a decrease in stability. So the important thing here is to determine when the bridge migrates into a situation where certain measures have to be taken. And that's why this extensive monitoring, it's a pilot project. It's within the context of a so-called European Union Smart City approach. So there's a lot of sensors mounted here. We have about a span width of 30 meters. Here are the pillars you saw on the picture before. Here in the middle, the pillars. And so each bridge field, 1, 2, 3, 4, has a width of about 15.3 meters. And on each of these, we have installed 2 tilt sensors. Then in the center, a strain gauge measuring the stress that's on the concrete. And again, 2 tilt sensors here. So if the bridge starts bending in the middle, we have basically 2 shoulders observed by tilt sensors, the strain in the middle, and where there was a crack, there we had installed crack sensors. In addition, there were temperature sensors with probes that were drilled at certain depth into the concrete to not only observe the ambient temperature that the nodes collect automatically already, all the nodes basically, but also to know what kind of temperature you would have within the bridge. The whole system then, we have pictures here, how the installation was done. Basically, the surveyors from the municipality of Dortmund, they did a stakeout of this pre-stressing cable that's lined in the bridge, and by laser, rotating laser, you see this light green stripe. All the sensors were exactly aligned onto this direction of the bridge. Here the installation of a strain gauge. And then, of course, where there were cracks, in addition, we had crack sensors, which you have already seen on the in the projects before. And here you see basically the whole installation. Here on this bridge field, 1, 2 tilt sensors. In the center here, a strain gauge, and then tilt sensors. Again, same on this bridge field here, and that same parallel on that side. So again, here, overview, tilt sensors here, center strain gauge, and then tilt sensors there again. On this line, on the outer, basically below the outer lane of the bridge, where the majority or the majority of load was expected. Now, what's special with this project here is that then about half a year later, after the system had established, at that time running on about half an hour data rate, a load test was carried out. And for this load test, a 48-ton crane from the fire brigades of Dortmund was placed at predetermined spots on the bridge. And better picture here, it's a huge crane and then they had exactly marked the place where the truck had to stand to cause a controlled maximum load at a certain point where we exactly knew what was going on. And during this time, we switched the system on the nodes on a 30-second data rate and switched the system to live mode, so that we could actually see when the impact of the load would hit the bridge, see when it would stabilize, observe it for, let's say, half an hour, and then move the truck away and see how the bridge returned to its previous position. And of course, then everybody, including the Dortmund press, newspapers, and so were there to watch, interested on the live data. Here you see 2 nodes tilting immediately after the truck was positioned, tilting in one direction, and 2 other nodes, tilt nodes, tilting into the other direction. Here a little bit closer, you could see how there was immediate reaction in the tilts. And as expected, 2 nodes on one shoulder tilting in one direction, 2 nodes on the other shoulder tilting in one direction. And you see how the strain on the bridge unit is microstrain, so a thousandths of a millimeter per meter, would increase in the center where we had the maximum deflection on the bridge. Now, what's so specific is, of course, that on one hand, we had now the test and saw that the bridge, the sensors were reacting. So the magnitude was that it could be picked up. In addition, there was an elaborate geodetic survey going on with these 3 Zoller and Fröhlich scanners, each of them far more than 100,000 euro, permanently scanning, and then, of course, scanning in a way that we had millions of points. So we had the whole area observed in very detail. And during this time, of course, then still observing that the scanner itself was stable, and everybody was quite interested whether also there was deflection enough that actually the scanner would pick up the signal. This guy here actually wrote his bachelor thesis about that, so I picked some pictures from his bachelor thesis here. And here you see the deformation of the bridge from the data of the laser scanning. So here in blue, you see the deformation of the bridge when the truck was placed on the outer lane of the bridge. And here, this is the line of our sensor nodes, the wireless sensor nodes here. And they now calculated from the deflection they had here from laser scanning, they calculated curves and the same curve they calculated from the tilts of the sensors and displayed them here. And you see that the results coincide quite well here. The comparison of the green dots from the tilt sensors and the blue dots or blue line here from the laser scanning. Now, when the truck was then moved to the inside, we expected less impact on the bridge, and of course then less signal here on the nodes. And we have another picture for that. You see that the impact is not that significant anymore, or you don't see this strange or the strong change in color anymore. Also, the signal is much smaller, but you see that both lines still coincide very well on the lower than millimeter level. And that actually is for both sides, the laser scanning and also for the node behavior, is a confirmation that these techniques fulfill their task. The laser scanner getting the whole area and a very detailed picture of the deformation here, but obviously laser scanning can only be done temporarily, so this cannot be permanently installed. But this is also verification that the permanent observation of this bridge by the sensors indicates valid behavior. And so the suggestion would, of course, then be that to define some alarm thresholds, that an alarm would be triggered when eventually this trigger value is exceeded, and that would then cause the surveyors to go there and do this scan, compare it with the reference scan, and then nobody has to be permanently or regularly going there, but the system would, the automatic system would fulfill this observation task. Basically, to finalize the whole thing, I here showed a number of sensors that can be connected. Of course, there's a huge variety of other sensors, like, for example, this is Rozennood Bridge near Amsterdam, where this supportive structure was erected underneath the bridge. And in order to determine when actually the bridge puts load on this structure, there are load cells like this one here installed underneath. So there's a certain signal when the bridge comes down that here you would see an increase of pressure. These are load cells, for example, that go up to 1,000 bar, relatively small by installation. This is millimeter values, so 15 by 8 millimeters size of this thing. And so this could be used for earthworks for this kind of structures also. Also, digital devices like this in-place inclinometers to measure below surface ground movement connected to this digital node here in Israel installed, can be installed. And basically there is no limit to the type of sensors that can be connected to these kind of nodes that can then communicate all together their data into the same platform. Well, to summarize it up, basically the idea of this multi-sensor systems is to measure a large variety of parameters depending on the demand of the customer. Whatever parameter he needs to observe can be connected to a node. The node communicates them among each other and transport the data all together into the same platform. So everything comes out of the same hand: tilts, distances, strain, pressure, temperature, things like groundwater or pore pressure, soil humidity, or weather stations even for precipitation or something like this, all comes from the same hand. And the important thing from our point of view, of course, it's all wireless, so easy to install, low maintenance, and longevity, as the nodes, for example, have battery lifetimes beyond a decade at a 30-minute data rate. So that's all I have to say today. I think I'm pretty good in time. Of course, I'd like to invite you to our booth at InterGeo, or InnoTrans or wherever you have the chance to meet us and have a look at the equipment. That's it for the moment. Thank you for your attention.
Thank you, Markus. Let's have a look and see what questions have come through. Okay, so first question is, how many sensors can be integrated?
Well, basically the number of sensors that can be integrated is unlimited. Into one site or project, we can have a multitude of sensors. One gateway can maintain up to 100 nodes, and then depending on how many sensors itself are mounted to the nodes. So the project can have unlimited number of nodes. The gateway can maintain 100 nodes.
Okay, thank you.
And many gateways can, of course, be in one project.
So let's see. Someone's asked, do we have access to gateway or remote platform to control the sensors remotely?
The answer is definitely yes. Things like, for example, recording rate or so can be manipulated via the online platform. Certain parameters, for example, on the gateway can be accessed remotely, but like transmission rate of the gateway has to be changed by our customer support. But in general, you don't have to go to site to change things like
that. Okay. Another one is, can these sensors measure absolute displacements, or can they only detect relative displacements?
I would be interested what's an absolute displacement. So basically, of course, monitoring is always relative, meaning you have a reference measurement that can be a certain value, 100 meters, and any deviation from 100 meters, but usually you baseline the value, you put it to 0 and see how it changes from that value. So absolute measurements like I would consider, for example, if you put a GNSS receiver on top of an object where you have an absolute coordinate, no, we can't do that. We have no sensor or no device that measures absolute absolute position. Everything, but I would consider that even if you do it with a total station or with a GNSS device, you would actually be interested in the displacements, and that's always a relative value.
Okay. Someone else has asked, can data be exported from the Sensieve platform to third-party platforms?
Definitely, yes. There are different ways of doing that. One is sending the data, pushing the data from the platform via FTP upload, or the other way around via API access to the Sensieve database and pulling the data out there into third-party platforms like, whatever, like Geomos, Trimble 4D Control, or other platforms like Safeguard or Mission OS or something.
Okay. Another one, can users provide their own sensors, or do they have to be purchased via Sensieve?
Well, it's definitely, let's say it this way, when somebody suggests sensors he has already at home or on the site, we would have to check whether we already tested them. In general, yes, it's only the type, the signal type, whether we can read the signal type, like it's vibrating wire or potentiometric, millivolt, volt, or even the digital signals from weather stations or in-place inclinometers or something like this. And we would just have to figure out whether we can read the signal. And then, of course, we need to maybe provide a certain plug to plug into our unit. But yes, customers can also provide their own sensors, and they can be usually connected to our nodes of the specific sensor type or a signal type.
Okay. So this is the last question. Someone's asked, you mentioned a 2-second reporting rate. What impact does that have to battery life of sensors?
Well, at 2-second reporting rate, I would expect a tilt node to operate about 2 years or something like this. Generally, at 30 minutes reporting rate, we assume 12 to 15 years of battery life, but 2-second reporting rate, usually this is only done for very temporary observation. So let's say for a week or something like this, and then they switch back to a different reporting rate. So that doesn't strain the battery, but if it's permanently on this high reporting rate, it's of course reducing the battery life.
Okay.
It's also a 2-second reporting rate, of course, requires different power supply to the gateway. That needs some consideration of the data rate that can be transmitted via a SIM card. Maybe better way would be to go via USB or RS-232 gateway onto a local computer then. But it's possible from the point of view of the nodes to go to this high data rate.
Okay, so we've had a few more questions come in, so I'll go through those. Someone's asked, is there a possibility to receive the data directly from the sensors to our own dashboard and not receiving the data via Sensi?
Yes and no. The data, I mean, the idea is wireless transmission, data communication. So the data always has to go to a Sensi gateway, but as just mentioned, we have USB or RS-232 gateways that can be connected to sensor hubs, or directly USB gateway could be connected directly to a PC, and then you have a local system where the data goes directly to the gateway and then from there onto your local computer. It always has to be considered that then, of course, maintenance power support is obviously more difficult, as it's not bypassing through our system. And the other thing is that, of course, then in our platform, of course, we can do calculations or pre-calculation, convert values, let's say vibrating wire frequencies into strain or something. When you read data out directly onto your own platform without going through our web monitor platform, then all additional calculation has to be done on that computer. Yeah, so you just get a vibrating wire frequency and a sensor temperature, and then you have to do the appropriate calculations to get strain, for example.
Okay. Okay, last 2 questions. Are you planning to support other sensors?
Well, we are always open to support any kind of sensors. We recently, I think October last year, we released the digital node, which opens, of course, the gate to a number of different types of sensors, where, of course, then we would have to establish the appropriate protocol to read the sensor. That might take a while, but on the other hand, any type of sensor, suggest one and we see whether we can read it. So yes, we permanently increase the number of sensors that we have experiences with, and of course we plan to increase that further.
Okay. So last question. What is the wireless range of sensors to communicate with the gateway?
I knew that this question was coming. We could actually have a whole discussion about that. I'll just move to one slide for that. I move to this slide again. So First of all, there are two different systems. You see, in both cases, we have the possibility of going or having nodes with external sensors and nodes with internal sensors. The one we always prefer is the flat mesh system, which communicates on 2.4 gigahertz, basically the Wi-Fi frequency. And anybody who has Wi-Fi at home knows what the limitations of Wi-Fi are. So I would say the longest distance I have between nodes on any project that I'm involved is about 170 meters. But of course, this is directly ruled also if there are obstructions in between. A Wi-Fi signal doesn't move through a thick wall or so the distance can be quite small and is obstructed anyway. On the other hand, it can be quite long. The advantage here is that one node, each node acts as a repeater for the adjacent one, so you can stretch the whole network over large distances until the data set goes to the gateway and then transmits. On the other hand, we have the Geo1 system, 868 megahertz, lower bandwidth, but with the lower or the longer wavelengths, you can go up to what I'm told, up to 15 kilometers. We have experienced in urban areas up to 4 kilometers, but then they are not connecting among each other, transmitting directly to the gateway. Both systems have their advantage and justification. Here you have much more flexibility, higher data rates, higher bandwidth, two-way communication to change the reporting rate on the nodes remotely, while this is a little bit more stubborn, but has good penetration, the system here, through objects like walls or so, or much longer distances. So we can cover kilometers between nodes, or if we have cluster, then we are limited to a couple of tens or even 100 meters. Here, we would usually take care that we have a certain redundancy between the nodes so that we don't stretch the distance between two nodes to the extremes, but to cut it in a way that even if this node fails, the distance to the next but one node can still be covered. So several tens to up to kilometers if you choose the appropriate system.
Okay, perfect. I think that's all the questions. I think we've covered all of them. Obviously, if anyone does have any more questions, please feel free to email us at info@senseed.com and someone will get back to you. As always, please keep a lookout for our September webinar, which we will be announcing soon. So thank you again, Markus, and thank you to everyone who joined us today, and I hope you have a lovely rest of your day. Thank you so much. Bye.
Thank you all. Bye.